Okay, hey everybody. So I know last week there were a bunch of issues with the connection. I have changed the stream settings to be low latency, which I suppose means the video quality has been reduced. So before we start, if for those of you who are watching right now, if you can read the text on the screen, that's fine. But if you're having issues, like maybe it's pixelated or something, do let me know. I think I can go back and change the settings, but yeah, I wanted to make sure it would be smooth this time. So yeah, let me know what you think. And okay, so I will get started then. Today we're going to do something different based on one of the suggestions from Piazza. We will be implementing a transformer. Okay, I shouldn't say that. We'll be implementing a very simple version of the transformer. And really, like, what is the important thing that we need to teach here? It's mainly how we parallelize the computations of the self-attention. The rest of it is just, stacking up many layers, adding things like dropout and layer norm and so on. That's all like not very, I mean, those are just modules that you add in pytorch, and you can, it's of course important to understand how they work, but the main advantage of the transformer is its parallelization during training time. So that's what we'll focus on here. So there are two different collab notebooks that I linked on Piazza and on the website for those of you who are watching, or for those of you who are going to watch later. I think these kinds of classes will go better if you open up the notebook and try to follow along and get the code to work. So let's start with this first notebook, CS685 attention exercise. The goal of this notebook is to create a self-attention network that's going to perform a simple classification task. So here we're doing spam classification. So we're using our transformer as an encoder here rather than as a text generation model or something like a language model. We'll switch over to that in the next exercise, but I just wanted to illustrate kind of the basics of how you efficiently compute attention, and this is a very simple task that's good for this purpose. Okay, so I've provided you a bunch of scaffolding code here just because we went over a lot of this stuff when we did the implementation of the neural language model. How do you go from strings to sequences of indices and then format those into the proper way to get them into PyTorch embedding objects and so on. But let's just quickly review. So here we're importing torch, and then we have these 4 sentences of data. This is a task of spam detection. So we get 3 instances of spam. You want $1 billion. Click here for midterm answers. Send me your bank account info. And then 1 instance of not spam. So read important CS685 news. So the goal is, of course, to predict that these 3 are spam and this one isn't. And for all of these exercises, we're not going to be doing any sort of test time prediction. We're just going to be looking at the training loss. But I'd highly encourage you, especially for the second exercise, to spend some time implementing a sort of decoding process. You can experiment with greedy, beam search, sampling, etc. That'll be kind of informative for learning how these things work at test time. But anyway, so we have these sentences, we have these labels. This chunk of code essentially splits up these sentences into tokens and then puts them into this vocab along with an index associated with each unique word type. And then this inputs object at the end is going to contain the list of indices that corresponds to each of these sentences. And again, feel free to ask if anything is unclear in the chat box. I think this kind of lecture is maybe a little difficult to do in this live stream setting, but I'll try and take any questions that come up. So anyway, this is what our input looks like after running the cell. We have these 4 different lists, one corresponding to each sentence, and you can see that some of the words here are reused. Word 12, for example, is CS685. It occurs in 2 different sentences, and so on. Okay, so now there's some scaffolding code for our neural network as well. This we're calling a self-attention NN. And remember, its goal is to be a classifier. So we have this init function, which we looked at in the previous implementation class. This is where we initialize all of the parameters of our network. So we're going to have an embedding layer, of course. This is going to be for the word embeddings. We're going to have, in our very simple network, a projection matrix for queries, keys, and values. So we're just going to be looking at a single layer self-attention network here. Once we get our values, we're going to then feed this to an output feed-forward layer to compute the predictions. This is just a binary classification problem. Is the input spam or is it not spam? Okay, so these are all the parameters that we have, and we have some different types of attention. The only one we're going to be implementing today is this dot product attention. There are other functions here that in your free time you might want to play around with and implement yourself, but we'll just go with the simple dot product. Note that the transformer in practice uses the scaled dot product. All right, and we've also given you some code to get started in the forward function here. So the forward function takes a single input, and that's like one of these sentences. So let's just go ahead and print this out to see what it looks like. So it gets as input the first sentence here in our batch of our data set of 4 sentences. And this is, again, a PyTorch tensor object now, so it has a size. Yeah, we're going to get the number of tokens in this input and store it in this n variable. So this is going to be the length of the input sequence. Now we're going to embed these and get a matrix of size n, the sequence length, by the embedding dimensionality. Okay, so now our basic architecture of this network is going to be, we're going to project these word embeddings to query, key, and value. Then we're going to do the self-attention computation for each embedding. Then we're going to somehow compose together all of the resulting output embeddings for each token into a single vector and pass it to this output feed-forward layer, which is going to give us our prediction. And down here, we have a training loop. This is similar to what we looked at in the previous implementation lecture. We've specified the number of epochs as 10. We're using the cross entropy loss. We initialize our network with, what is this argument here? An embedding dimensionality of 20. And we have 2 possible outputs, spam or not spam. And this is the length of our vocabulary, the number of word types that we have. We're going to train this using stochastic gradient descent with a learning rate of 0.01. And then this is just a standard training loop. It's doing backprop on the cross entropy loss and updating the parameters, zeroing the gradients, and printing out the loss of this classifier at each epoch. So our expected output for this exercise is to see this loss go down to somewhere close to 0, which indicates that the network has at least overfit this tiny 4-sentence long training set. All right, so that is a kind of quick overview of the code that's given. Now let's get started with some implementation. So we've initialized this attention reps matrix, which is the same size as the embeddings matrix. And this is going to be where we store our final attention kind of weighted average of each token in the sequence. So I have n number of tokens, and for each of these n positions, I'm going to get a weighted average of the value vectors, which I'm going to store in the corresponding row. Okay, so let's get started with probably the simplest and dumbest, but easiest to understand way of implementing this kind of self-attention computation. So the first thing that we want to do is pretty easy. We're going to just project these embeddings into the query key and value spaces. And we're going to do that by using our matrices that we've created up here, these linear layers. So I can do this by just passing in ems here. So this is going to give me another object of this size. I can do the same thing with the keys. It's the same dimensionality. I'll just write that. And the values. Okay, so I've got these three different projections. And now I want to start computing the self-attention. And so the way I'm going to do this is, of course, for each query embedding, I want to compute the dot product between that query and all of the keys. And then I want to apply the softmax. I want to then take the weighted average of the value vectors, and I want to store that in this attention reps function here. So let's take a look at how to do this with a very simple and slow solution. So simple, slow solution for self-attention computation. And of course, because it's slow, it's going to start with a loop. So I'm going to loop over every single position in the sequence. So we know that n is the length of the input sequence here. And at each position, I'm going to take the current embedding as the current query embedding and use that to compute this dot product against all of the keys. At each iteration, at each position I, take query q sub I and dot product with all keys. Not good English, but you get the point. So we can do this pretty easily by using the matrix vector product function in pytorch. So my unweighted, I guess I'll call this my norm scores, is just going to be torch.mb. Note that this function is a matrix vector product, so the first argument here should be the matrix, which is my keys. Again, this is n by dm size matrix, and my query at this particular position is queries I. This is going to be my vector. So we would expect this to return a single score for every key. So this vector should be of dimensionality n. And oops, Python 2 syntax creeping in. Let's see what happens here. So yes, it does print out a single score for each of the different keys for this particular query. And now, again, these are unnormalized, right? This is not a probability distribution. So I can convert it to one by calling torch.nn.functional.softmax, and I can apply it to my these unnormed scores and along the first dimension. Sorry, these help boxes are covering up the code that I'm writing. So now if I print out these probabilities, I get an actual well-formed probability distribution. So I've successfully computed the attention scores for the very first time step, right, when I is 0. Now if I loop through this till I equals n, I'm going to get these probabilities for each position in the sequence. The only thing that's changing here is what query embedding I'm using. Okay, so hopefully this makes sense so far. And now the next step is, of course, to take our attention weighted average of the value vectors. So there are many ways in which you can do this. Probably the most straightforward is, I mean, this essentially can be done with another matrix vector product. So if we want add values, we can do torch.mv, and here we can do this, which will give us an attention weighted average of the value vectors. There's an alternate solution, which is probably more straightforward to understand, where actually I should take that back. It's not as straightforward to understand, but it introduces an important concept, which you should certainly understand. So values here, God, these help boxes are annoying. Values times probabilities. So this asterisk means we're doing an element-wise product. So every single element of the values matrix is being multiplied by this probabilities, this probs vector. So of course this doesn't make sense, right? Because values is a matrix and probs is a vector. So they don't have the same number of elements. I can't just do an element-wise multiplication. But that's where this very important concept of broadcasting comes in. So I want to essentially multiply each element of a row in the values matrix by the same probability, right? And then I can sum over all of these element-wise products over the rows to get my attention weighted average. So to kind of duplicate this probs vector across this first dimension, I can do broadcasting, where I say that essentially I'm putting in this none argument in the second axis. So this is normally how we index PyTorch tensors, but none here indicates that I want to broadcast the same value in this first dimension across the second dimension here. So this is going to allow me to do an element-wise product between this matrix and this vector, because this vector has been broadcast into the second dimension. So once I do this element-wise product, I'm going to sum over the first dimension, which is going to give me my weighted average of the value vectors. So these two things are equivalent. I won't belabor the point. You can try them out afterwards and make sure you understand what's happening here. But both of these are just ways of getting the weighted average of the value vectors using the probabilities that we computed as the weights. Okay, so we'll go with this one for now. And we're just going to store this thing into our attention reps matrix at the corresponding dimension. Okay, so we did this, and now we're going to first, there is of course a more efficient implementation of the attention, which we'll get to a little later. But for now, we're going to just connect this attention reps into our classifier and make sure that the loss is actually going down. So making sure that we've done this properly. So the last thing that I need to do is, now I have attention reps, which is n by dm matrix, and I want to get it down into a single vector that represents the entire sequence before I feed it to this output. Compose attention reps into a single vector. So there are many ways you can think about doing this, but this is a very simple example, so we'll just simply average. So we can do torch.mean attention reps 0. Oops, should be dim equals 0. So we're going to average across the sequence length dimension and get a single vector that's of the size of the embedding dimensionality. So if I print this, for example, I get just a 20-dimensional vector, which is the size of my embedding dimensionality. So, I mean, we've talked about many other ways of composing multiple representations into a single one. In BERT, we wouldn't even have to do this, right? Because we would just index the CLS representation and feed that into the classifier, but we're not using BERT here, so we have to train our own thing. And now we can just use the existing code here, which feeds in this composed vector into the output classifier. Okay, so if we train this function, all right, the loss is going down, but not too much. Maybe we can try increasing our learning rate. All right, so that helped. So we can see that our loss function went from somewhere close to 3 to down to 0.12. Of course, if we train with more epochs, we will likely get to something very close to 0. Okay, so I've just shown you this incredibly slow and solution for self-attention that you shouldn't use in practice, and that no implementation of the transformer, like the pytorch default, for example, doesn't use this either. But now let's get into a more efficient implementation. I guess before that, is there a way for us to keep track of tensor size besides putting them in comments? I usually just put them in comments. I guess if you're playing around with it, you can come up with some other way, but yeah, I'll try and be better about putting them in comments. Can you explain how none works in broadcasting here? So, right, none, when you're doing broadcasting, essentially means you want to make a new dimension and copy this thing over. So let's maybe, I think to explain this, I'll show a simple example. Just do it in this loop because why not? So let's say that I have a matrix of ones. This is going to be all ones. And let's say it's going to be 5 by 5. So does this work, first of all? Let's see. Okay, so we have this matrix. And now let's say we have this vector. Let's say it's going to be a, I think this is all I need to provide. Okay, so I have these two vectors, and I want to multiply them together. Oh, I think I should make this a float tensor. Maybe I can do that like this. Yeah, okay. So so basically, if I want to multiply or take the dot product between this, so like, so let's just look at where the broadcasting is used in our example. We're using it to do this element-wise product, and then we're summing after that. So let's take a look at what happens if I apply the same computation. So I basically want to multiply every row here with this vector. That's my goal. But of course, I can't just do an element-wise product because these are different dimensions, right? So broadcasting explanation. So let's just first of all make that clear. Oh, so this actually did the broadcasting automatically. So this is what we want to happen. I didn't realize that it would automatically do that. But usually in something like NumPy, you'll get an error when this happens because this vector is not the same dimensionality as the matrix. And so what you do with none is it essentially just duplicates this vector row-wise into a matrix such that you can actually do this multiplication. So this gives you the, interesting. So yeah, it depends on what dimension you broadcast into. So I think this would be the equivalent of the pytorch case. So actually, this is a good demonstration, right, of what's actually happening. So okay, so maybe I should print mat, print vec. So here, if I apply the none to the first dimension of this vector object, then it basically takes this and multiplies it with each row of the matrix, right? So it's expanding in the row direction, which means the broadcasting operation essentially just copied this into 5 different rows of the 0, 1, 2, 3, 4. And that's why you see the output product is just 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, and so on. However, if we use this operation, it's going to do this multiplication column-wise. So here, we've instead made a matrix where each column in the first, so each element in the first column is 0, each element in the second column is 1, 2, 3, 4, and so on. This is what is happening, and the none is essentially telling you which dimension you want to copy over. You can think about it that way, although in practice, nothing is really being copied in memory. This is an efficient way of duplicating your data in the matrix without incurring memory penalties. Okay, if you use a matrix size that isn't a square matrix, your code, okay, maybe you're right. But yeah, we won't go into that here. We are essentially converting a 1D row vector into a 2D column matrix and broadcasting. Yes, that's the intuition, although under the hood, that's not actually, so there's nothing being copied. But yeah, that is implicitly what's happening here. Okay, so I'll comment all of this out. You can feel free to play around with it. But you'll see in other implementations, which are more complicated, actually have a batch size of more than 1, there's going to be a lot more broadcasting going on. It quickly becomes hard to even keep track of what your dimensions mean and which dimensions you have to broadcast over. So yeah, it is something that requires a lot of practice to get good with. And this is why every time you write a new line of code or a new computation, you should have some sanity checks to make sure that it's doing what you think it's doing, because as you can see here, even broadcasting across the wrong dimension is going to alter your results. So you need to be careful and make sure you got everything right. All right, wow, so I've already used 27 minutes. This is proceeding inefficiently as usual, but hopefully broadcasting is now clear. So now let's get to a more efficient implementation of attention that is not using this for loop. Okay, maybe I'll move this out of the loop just to, I'll put it down here, so, okay. So now let's go ahead and comment out this part. Oh, there was a question that I missed. Can you explain the compose step? Yeah, so remember that this is just a simple sentence classification problem. So when we do our weighted value vector average, we get a different value vector for every position in the sequence. So now we have n different vectors and one for each word, but we want a single representation of the sentence to pass into our classifier. So the compose step is essentially any function that will take a sequence of vectors and produce a single vector. So we just use the element-wise mean here. Okay, so we did our slow version. Now let's do a efficient computation. So I guess I probably will spend less time explaining this, but we're going to do our implementation in the dot product attention function, which is up here. So this function is going to take all of the queries, the keys, and the values as arguments, and we're going to compute this attention reps object without any for loops. So that's our goal. If we can avoid using for loops, we take better advantage of the GPU. We try and vec possible and avoid loops wherever possible, as it just takes better advantage of the GPU's case. So here, note that all 3 arguments our n by dm matrices. So we don't have our queries as a vector here, and we were looping over our query matrix before, but now we're not going to do that. So the very simple change that we're going to make is back down here, we took a matrix vector product, but here we can just do a simple matrix multiply to the key matrix, and this gets all. Said it was disconnected. Hopefully it's reconnected now. Anyway, so here the high level intuition is essentially we replace these matrix vector products with a single matrix multiply, which allowed us to efficiently get all of these dot products at once. So this is the important line in this code. Okay. Hopefully the connection improves. And now if we, okay, looks like it's back. If we run this, we see that our loss is still improving. And we should make sure that these two things are giving us the same results, right? So let's take a look at that. Results, right? So let's take a look at that just to confirm. So I'm going to uncomment the slow solution. Let's say I'm going to call this attention reps 2. And let's just see if print attention reps. Oh, these are probably pretty large vectors. Let's just look at the first element of each. Okay, slow attention. And then fast attention. Oops, and this should be attention reps 2, 0. Okay, so hopefully we'll see that these two are this. That was dumb. What was I doing here? Okay. All right, so hopefully we see that these are the same. And they are the same. So this is just showing that these two methods of computing the attention are equivalent. And so if you're still a little unsure about these computations, you can go back to this code and make sure that you understand what's happening. But I do want to switch over now to the text generation example, as I think that will show you how to actually efficiently implement the masked self-attention, which is something we haven't talked about as of yet. Okay, so at this point, if you could switch over to the second notebook here, the transformer exercise. Let me make sure it's switched over here. So this is, in this example, we're going to look at a slightly more complicated task. So as you can see up above, we're going to be giving a network a sequence of characters like AA, BB, CC, DD, and we're going to ask it to generate the same sequence in reverse order. So of course, with a very simple vocabulary of like 4 letters, this is going to be a very simple task, but this is actually not a trivial task if you have huge. Okay, so the goal of this exercise is mainly just to explain the masked self-attention and how you can compute it efficiently. So let's take a look at, there's again some scaffolding code here. First, we are creating a small data set here, at least bigger than before, 500 examples. It would encourage you to actually try this of training on sequences of length 10 and then testing on sequences of length 15. But in this lecture, we're just going to focus on the training case. Yeah, it is buffering a lot. Okay, let me quickly try reducing the video quality. I think I can still do that. Okay. All right, hopefully that helps. Do let me know if it's still not working. Yeah, sorry, I did try and figure out what was going on with my internet, but could not find anything wrong. So hopefully it doesn't mess up anymore. Okay, anyway, so here I have a vocabulary of A, B, C, D, E, start of sequence, end of sequence. Note that now that we're doing a generation task, we need to have these start and end symbols for the reasons that we discussed in language modeling, right? We need to know when to conclude the decoding process, etc. This code essentially is just getting all of our sequences into the correct PyTorch format. One thing that's important to note here is that we have a sequence-to-sequence model. So we have an encoder and a decoder. And when we're doing text generation with a decoder, it gets an input at every position, which is kind of the shifted sequence of what it's actually predicting. So just to explain what that means, if I want to reverse this sequence that's in my training data, D, E, E, A, E, blah, 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 and it ends with the end of sequence symbol, I have two different things that I'm interested in with my decoder. One is what is the input to the decoder? And remember, during training, we're passing in the ground truth sequence into the decoder. So the first time step, the decoder gets the start of sequence token. And the target is what the decoder is trying to predict. So it's trying to predict E, which is the last word of this sequence. And then the next input is E to the decoder, and it's trying to predict the next word of the sequence, which is E. And then it gets in the ground truth next word, I should say character here, and it's trying to predict the next character D here. So hopefully you understand the distinction between the input of the encoder and the target. You can see that the target is just shifted over by one position. So we're not predicting the start of sequence token ever. We are only using the start of sequence token as input to our decoder at the first time step. Hopefully that's not confusing at this point, but if it is, feel free to ask and I can clarify it more. Okay, so again, we have a training loop. I'm not going to go over this. You can look at it if you're interested, but it's just computing the cross entropy loss at the sequence level this time. So since we're making a prediction at every time step, we're going to take the average cross entropy loss at every position of the 500 sequences that we have. So that's all I want to say about this first cell, and all of our work will be in the second cell, where we're going to be focusing strictly on the decoder for this task. Okay, so let's take a look at our init function here, where we're going to set up our parameters. So we have, this is again just a one layer thing. We're not looking at multi-head attention, just single head attention. But all of these are very trivial modifications over this base code base of like efficient masked self-attention. So we have our character embeddings. These are like a substitute for word embeddings. But here, obviously, we're not using words, we're using characters. And we have position embeddings. And so here, we're not using the transformer method of the sinusoidal hard-coded embeddings, but rather we're just creating another randomly initialized word embedding object, here, and I've just arbitrarily made 20 of them. So every position from 0 to 20 or 19, I should say, is going to be associated with its own word embedding that's going to be learned from scratch. This is the same method that BERT uses for its position embeddings. It doesn't use the sinusoidal embedding function of the transformer. Okay, so we have our query key value projections like we did in the previous exercise, and we have our softmax layer. Okay, so here I've also copied in some of the code from before. We have our DOM slow attention, which is what was in the for loop from the previous exercise. So this assumes that your query is a single vector, Q, and your keys and values are matrices. We have our fast, efficient version of this, which we call smart unmasked attention, which is doing the same computation as we saw in this dot product attention function. So here, the query, this is going to be used for our source attention, where the keys and values are going to come from the encoder and the queries are going to come from the decoder. So with that, we get the scores of the and then what we're going to be implementing here is the masked attention, which is going to be used for target side self-attention in the decoder. So that's what we're going to focus most of our time on implementing. Okay, so let's go through this forward function just to see what scaffolding code is already here. Our input here is now no longer, well, let's take a look at the input just to see what it looks like. So it's a single sequence as before, and the first dimension is going to be the batch size, the second dimension is going to be the length of that sequence. Which in our first cell we set to 10. All of our training examples are going to have length 10. These are all 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 character long sequences. Okay, so we get this thing as an input, and we first are going to get the position embeddings for each of those 10 positions. So that's in this posems object. And we're going to take the character embeddings associated with the input, and the first thing we do is add the position embeddings to those character embeddings. So this is, again, what is happening in the transformer. And so for the encoder, I didn't want to focus on this at all because it's not important. So we're just going to do the value projection and assume that those are the output here. Of course, you would want to, so exercise to try at home, implement self-attention for encoder. This should be very straightforward. Actually, if we have time at the end, we can do this. But the masked self-attention only happens at the decoder, so we're going to focus on that. So for the decoder, we do the same thing that we did before. We get the character embeddings associated with the decoder inputs, which is confusingly named outputs here. Maybe I should rename this to decoder inputs to be more consistent with the thing that I printed above. We're going to add the position embeddings to these, the same set of position embeddings, and then project to query, key, and value. So this is where we start. And now the first thing that we want to do is compute the self-attention on the decoder side. So remember that this is not as trivial as what we saw in the previous exercise because we want to avoid cheating, right? We don't want the attention weighted average to include value vectors that occur at time steps that we're not currently at yet, right? Because we don't want information about what comes in the future to influence our network. Otherwise, it can easily figure out, what it needs to predict. So, okay, how do we get started? Again, just like before, we're going to start with an inefficient solution, which hopefully makes it clear what we're what we're doing, and then we're going to look at a vectorized solution. So to start with, I'll make an object called decoder states. I'm going to initialize this to max len by the hidden dimensionality. And I'm going to store each attention weighted average corresponding to each decoder time step in this decoder states matrix. Okay, so we can consider this n by dhid, of course. And now we're going to do our standard looping based solution here. So for we're going to loop over every time step in the decoder. And now it's not as simple as what we saw before, where we can just use all of the keys and all of the values to do this computation. Here we actually have to slice our keys and values to account for the current position we're at, because we don't want to cheat. So I'm going to create a new variable called previous keys, and I'm going to take the decoder keys. This is, of course, target side self-attention. Maybe I'll make that clear here. Target side self-attention in decoder. So the keys and values are just the previous hidden states in the decoder. And so I don't want to use keys that occur in the future. So I'm going to go from 0 to the current time step. So if I go to I+1, that's going to include the current time step, which I do want to include in my self-attention computation. I'm going to do the same thing for the values. So I'm just writing out the 0 to be more clear. Of course, you don't have to include it in practice. So this is going to include all keys up to and including the current time step. Sorry. And keys here is, of course, referring to these decoder keys. All right, and the same thing with the values. So an interesting thing here is that the shape of this previous keys and values is going to change as we increase the position that we're at in the decoder. So let's make this more clear. I'll just print the size of this previous keys object, and hopefully that'll make it more clear what's actually going on in this. So you can see that at the first time step, I'm only allowed to look at the current key, right? Everything else is in the future, so it's cheating to look at it. So I have a key matrix of size 1 by 50. In the next time step, I'm now allowed to look at 2 things. In the next time step, I can look at 3 things, 4, 5, up until the final time step where I can look at everything. So hopefully this is clear. I'm using a different number of keys every time to avoid looking at things in the future. That's the critical thing to take away from this. If you don't remember anything else about this exercise, oh no, quality is bad. Perhaps I should have recorded this beforehand and then uploaded it. Sorry about these issues. Okay, so it looks like I'm not connected. Hopefully it comes back soon. Okay, looks like it's back. Where's my... All right, so it seems to be better now. Okay, so we have this variable length of keys and values due to the ever increasing time step of our decoder. So hopefully that makes sense. And now we can just apply our dumb, slow self-attention that we already computed or implemented in the previous exercise for this. So I can do self.dumb slow attention, and remember this takes the current query that we're at, so d queries I, and it takes my previous keys and previous values as the keys and values, and then I'm going to put this into my decoder states matrix at position I. Okay. I mean, I could have just made this one line. That was dumb. Okay. So this is with the loop. And now I will go back to the efficient computation with the mask in a little bit. I want to just finish up this coding block and get to a point where we can train this network even with this dumb slow attention. ISP like Xfinity has really low upload bandwidth. Yeah, I'm on a Spectrum. I don't think it's great either. Anyway, so let's implement the source attention as well. This is pretty straightforward. Let's do source attention. We can do this just using our smart unmasked attention function, because remember, in the source attention we don't have any issue with cheating. We already have all of the information about our encoder's representations. Those don't depend on the current time step of the decoder. So I can do this by, what did I call this? Source attention equals. So now we're going to use our smart unmasked attention. We haven't yet implemented the masked attention. And this takes in as input the queries from the decoder side and then the keys and values from the encoder side. Queries come from decoder, keys, values from encoder. So again, this should be easy to understand based on all of our prior discussions of the source attention and transformers. We want some connection between the encoder and decoder, and this is what gives it to us. So now we have these two things. We have the decoder self-attention. Okay, sorry, it disconnected again. I was just saying that in the transformer, we don't actually use the query embeddings for the source attention, but we instead use the output of the decoder self-attention, which in this case is this decoder states variable. So this gives you a more contextualized representation of the decoder embeddings. Okay, oh, great, I'm not connected again. Okay, it looks like I'm somewhat connected now. So now let's go ahead and combine these two representations. This is also pretty straightforward. All we do is just add them together. So really nothing fancy here. Let's go ahead and print the size of these just to make it more clear. Decoder states dot size, source attention dot size. So these should both be the same size, which will, yeah. So I get for both of these an 11 by 50 matrix where each row corresponds to either the source attention representation at that position or the self attention representation at that position. And in the transformer, to combine the input from the source attention and the self attention, you just add these two representations. So combine decoder self attention with source attention. We're just going to add them, so I'll just keep it in the source attention variable plus decoder states. Okay, so now that we've computed both self attention and source attention, the scaffolding code will do the prediction in the softmax layer. One little thing that is not super important, an implementation thing, is that for the softmax, we're going to reshape all of the source attention hidden states into, I mean, this is relevant only if you have a batch size of more than one. But we basically flatten out the first two dimensions. So the matrix is of size batch size times sequence length by hidden dimensionality. Again, this is not relevant for this example since we have a batch size of 1. But if you want to experiment with larger batch sizes, this is important just for the way in which PyTorch deals with the softmax. Okay, so let's see if this works. Please work. Okay, cool. So the loss is going down, and that indicates that our network is successfully learning this this sequence reversal on the training data. Okay, so now just to get back to the most important part of this exercise, which is how do we make this faster? Okay, so how can we compute decoder self-attention faster? We can't just use smart unmasked attention, right? Because the mask is required to prevent us from cheating. So as before, we're going to do all of our code in the function up here. Where is it? Smart masked attention. So let me call this I don't know, fast decoder states equals self.smart masked attention, and this is going to take in my queries, my keys, and my values as inputs. Okay, so that's great, and now let's take a look at how we actually implement this. All right, so just like in the smart unmasked attention, we're going to be taking advantage of the matrix product between the query matrix and the key matrix, but we want to first apply a mask to the key matrix and the value matrix before we actually do this. So how do we actually do this? First, let's get the size of our query matrix again. So we basically just want the max length. And this is going to define our mask. And so remember, we went over how this mask looks, right? It's this lower triangular matrix where we essentially want to be revealing only up to and including the time step that we're currently at. So PyTorch provides this nice function called trill or trial or whatever you want to call it, that will give you the lower triangular part of an input matrix. So it's going to set all of the upper elements in the upper triangle to I think 0. We will see here. So to get all of the lower triangular elements to be 1, I'm going to put in as input a maxlen by maxlen matrix. This is one too many parentheses. So let's take a look at how this looks. So if you look at this matrix that was printed out, you see that this is actually exactly what we want. And we can compare this to the output of the for loop, which was showing us we had an increasing dimensionality of keys at each time step. You can view each row of this matrix as corresponding to one time step and which keys need to be masked at this time step and which keys need to be unmasked. So our mask is this matrix where the lower triangular elements are set to 1 and the upper triangular ones are set to 0, although we'll see that we need to change the zeros in a bit to be compatible with our softmax. Okay, so we have our mask. Hopefully that makes sense why we're doing this. If not, as usual, write a question. And so now what we're going to do is we're not going to use the mask directly to mask out the unnormalized scores, but we're going to apply this at the softmax. So I'm going to just copy this code from before. And so this is going to get all unmasked dot products at once. But now I'm going to apply this PyTorch method called masked fill, which is going to fill in every part of the scores matrix where the mask at the corresponding position is, and again, this is the same dimensionality as the mask, which is why we can do this. So mask fill lets you set the value of any element that where the mask has a particular value to a specific number. So here our mask has, where we want to change this is where the mask is 0. We want to set this to some very, very low negative number, close to negative infinity, because this is going to allow us, after we apply the softmax, to get these elements to something close to 0. So I'm going to use, to negative infinity, my bad, not, yeah, I think that's what I said. Okay, so some very negative number, which is going to let us, after the softmax, which I can also copy from up here, it's going to set all of the scores where the mask is 0 to 0 after the softmax. And let's take a look at this just to make sure it worked. Okay, so it's kind of messy, but you can see that for the very first sequence, it put 100% of the probability in the first key and 0 on every other key. So this is exactly what we want, right? For the second sequence here, or second time step, 66% probability on the first time steps, hidden state, 34% on the second, and 0 everywhere else. For the third time step, I guess it decided to put all of its probability mass on the third time step. But you can see that this has worked, right? The mask is successfully constraining the keys that we don't want to influence this distribution to 0. Which means that when we take the value attention weighted average of the value vectors, since the score is 0 for all of these value vectors, they're not going to come up in the weighted average. So hopefully that makes sense. And so finally I can just return this. So there's not much difference between these two functions. The key difference is with first creating this mask. And again, this is something that you could likely cache in your init function if you're going to have the same length inputs at all times, like we do in this trivial case. If you're going to have variable length inputs, then you probably don't want to do this. And you probably want to initialize it in the self-attention computation itself. And then the masked fill part is important because we're applying the softmax, so we can't just element-wise multiply mask with scores here. And you should also think about why we can't just take the softmax of the unmasked dot product and then mask the resulting scores. So actually I can show you this, although I don't want to waste too much time, but we're already way over. So let me just show you what happens if you do the other approach. So we have our unnormalized scores. We're going to get rid of this masked fill thing, and we're just going to multiply the scores with the mask. So what happens here? And this should tell you, whoops. So we see the issue here. If we do this if we multiply the mask with the scores after the softmax, we don't get well-formed probability distributions, right? Because the original distribution had summed to 1. Now we're masking out all of the elements except the first one, but the first element was 0 in the original softmax distribution. So when I apply this mask, I just get a vector of all zeros. In the second time step here, I'm only allowed to look at the first and second time step, and there's probability of 2% on the second time step, but there's 0 probability everywhere else. So you can see that this is not the way to implement the masked self-attention. This is why we need to compute the softmax only after we do the masking. Okay, so Yeah, I think this should, so this is the correct version. All right, so we've implemented the fast version of the masked self-attention, and now let's just, okay. I'm a little confused on the time step. Can you explain it again? Could you clarify what you mean by the time step? So just as a refresher, the decoder in this text generation setup is producing a single word at a time, right? So one time step corresponds to, if we go back up here to our data, at one time step, at the first time step, I get my decoder as input gets the start of sequence token as input and is asked to predict D. And so, of course, at training time, I have access to the full ground truth sequence, so I can parallelize all of these computations, but I need to ensure that at the first time step, I'm only looking at the key associated with this start of sequence position and none of the keys associated with any of these other time steps, because those are actually what I want to predict in the future. So that's the intuition. Let me know if that wasn't actually what you were asking, and I can clarify further. But I wanted to wrap up here with a kind of timing experiment just to motivate why we want to do this fast vectorized operation as opposed to the for loop version. So to do this, oh, and before we do that, let's just again make sure that these two things are equivalent. So decoder states, maybe I'll call this slow decoder states, and fast decoder states. Are these two things equivalent? We will shortly see. Let's just print out the very first time steps representation to see if they match. And yeah, they look pretty equivalent here. So the embedding hidden dimensionality here is larger than before, but you can see that these are identical. So the fast and slow versions are doing the same thing. Now let's, in the last few minutes, go ahead and time these and see if the slow one is actually slower than the fast one. So we're going to just use the pytorch Python time function. There are better ways of doing this timing. There are libraries that you can use that probably account for various confounding factors, but this is a decent way of doing this. Oh, and I should say start time equals time.time and smart time equals time.time minus start time. Okay, so basically I'm just timing everything that happens within these two timing calls. This is a little harder to do when we're on the GPU, although right now we're on the CPU. There's some possible synchronization issues, but this should be fine for now. So, okay, I want to print out the time difference. So let's just do this, dumb time. I see that I'm not connected. This is probably a good time to write this print statement. Yeah, that should be fine. And actually, I don't know what level of precision I should use here, but yeah, let's see what happens here, assuming I haven't made any dumb errors. All right, so our dumb time took, so this was the one with the for loop, took 0.0 seconds, I believe it's in seconds, to do this computation, whereas the smart one that was fully vectorized took an order of magnitude less time. So you can see that there are big benefits from parallelizing this computation. And I should also mention that an LSTM has to operate in this format where you loop over every time step in the decoder, because the representation at time step t depends on the representation at time step t minus 1. So again, this is one of the examples of why transformers are preferred over recurrent neural networks for these kinds of text generation applications, because we can parallelize entirely the decoder's computations at training time, and we can't do this with this masked computation with a recurrent neural network. Okay, so I guess that's all I wanted to show. Oops, let's just make sure that we can train this network again. So we'll use the fast decoder states here. Oh my God, fast decoder states. All right, so this is just printing out the time difference for every example in training, and you can see that the loss slowly goes down to under 1. With more training, it would certainly go down even lower than that. All right, so I know we didn't implement a full transformer here. To implement a full transformer, you would have to, first of all, make your encoder a real thing and not just a bunch of embeddings. Second of all, you would want to make these attention computations use multi-heads instead of just a single head. This is a straightforward modification where you can do all of this with a single matrix product instead of looping over your heads. Again, you want to avoid loops in your code whenever possible, so you don't have to do that for adding multiple heads. Third, we of course have some feed forward layers from the transformer block that we're missing. We also have dropout and layer normalization and residual connections between the layers that are missing, and you should feel free to add all of those things to this this example if you want. But the critical component of the transformer, and the thing that you need to make sure you understand, is how this masked self-attention works in the decoder, and how we're able to parallelize across the entire sequence without looping through it. Okay, so that's it. For next time, we'll be talking about applications of vision and language, so like multimodal tasks with a focus on navigation. So it should be pretty interesting, and see you then.